All right, so welcome in. Okay, so this is a test. It's a little bit challenging test, okay? So I hope that you take a look at it. And so there's about 5 questions, although there's several parts to certain questions throughout. Now, this test is assuming, okay, that you do have some knowledge on kind of work, energy, power. You've done work, you've done stuff on forces and kinematics as well. So both kinematics, dynamics, to be able to work with this stuff out. All right, so as usual, I'm going to put up the link to the test so you can download the PDF file for yourself and try it out. And then you can come back and then watch the solutions and see how well you have done. So let's get ourselves started. So here is the typical in these physics tests. So what I'm going to be assuming, I'm going to be rounding the answers ideally to the same number, okay, of significant figures as the lowest number of significant figures in the measurements, right? So try not to round in intermediate rounding or intermediate steps. So question number 1 is the following. So a stretcher is being pushed with a constant force of 75 newtons to the right for a distance of 15 meters. So I guess that's the displacement. A constant force of friction of 48 newtons is present, I guess, during the transportation. All right. Okay, so let's draw this out first. So let's do a free body diagram in here. So I know this is not exactly a stretcher, okay, but this will do for us. So what is happening here? So we have a force. So this is the force to the right. And this force is 75 newtons. Now we also have an actual force of friction, which is going to be in the opposite direction. So this always opposes the motion. And this one is 48 newtons. All right, so those are the two. Now we have our usual, so force of gravity, force of normal, although those will not be needed, okay, within here because those cancel off. Now let's take a look and see what they're asking. So what is the work done by the person pushing the stretcher? Okay, so this is the part A component. So the work done by the person pushing the stretcher, okay, so this is the constant force, okay, that we have, and that would be just this force on its own. So that's the total force applied of the person. Now, in order to be able to calculate the work for that, so I'm going to call this work A, so it's going to be work applied. So it still goes in with the force applied, and of course it's going to have to multiply by the actual displacement caused. Now the displacement in this question, it says it's 15 meters. All right, so it's being pushed for that. And that would have been the total work done by the actual pushing. So it's not very difficult for us to do that. So this is going to be 75 multiplied by 15. Notice both newtons and meters. So we're going to get our answers in joules, which is exactly what we want. So 75 times 15. And I'm going to just leave this for the moment, 1125 joules. Now, and if you were rounding, so this would have been 2 significant figures actually. So I'll put it in brackets, but I'm going to keep this in case I need it for the other items. Now, this is the actual work done by the person, right? So pushing the stretcher. So this is the actual work applied. Now, this is always sometimes tricky because very often people will want to be able to incorporate this force of friction. But if you're only asked for the force applied, then this is the only force. This is the work that it's going to be done. Now, of course, you're going to have to overcome that force of friction, but that would have been the total, right? So the summation of the work. Okay, so this is part A. So let's take a look at part B in here. So this is going to be what is the work done by the friction during the transport. So this is another good one. So this is the work on friction. So I'm going to put F for friction. So that's going to be the force by the friction multiplied by the displacement. Now notice that within here, so the original standard equation, okay, for work is always the force applied times the displacement times the cos of the angle in between. Now, when both the displacement and the force are in the same direction, then obviously this equals 1, and that's why I use this formula. Now, in this case, my actual force of friction, so which is this force, and the opposite side, is in the opposite direction. So if it's going to be in the opposite direction, then I do have to be careful, because that means it's going to be cos, okay, and the angle is 180 degrees, and this is going to be equal to -1. So that would turn out to be that this is going to be force of friction, which is 48, multiplied by the displacement, still 15, times -1, because it's in the opposite direction, and this would have been my total work done by the force of friction, which is in the opposing, right? So this is in the opposite direction, meaning the force is in the opposite direction. So this should give us a negative value, and indeed that's what we're going to get when we're going to do this multiplication. So it's going to be negative 720 joules. All right, so that's what we have there. Now, the next question, okay, or part is, what is the net work done on the stretcher during the transport? And this is always important. So what is the net work done, okay, on the stretcher? So that would have been both the force of friction and the applied force. So whenever you're working with these questions, do make sure to check, okay, so which work are you going to be referring to in general as you work these things out? Is it the actual work that is being applied, right? Or is it the total or net work, okay, that is done overall? Now in this one, in part C, it is overall. And in that case, if you're going to be doing the overall, so this is the work or the net, so that would have been the force net multiplied by the displacement, and of course times cos, okay, of the angle. Now in this case, notice that the net force, this is going to be nothing else but 75 minus 48, right? So this is going to be in the same direction as my displacement of 15, so I'm not going to worry about the cos of the angle because the angle is 1. The cos of 0 is 1. And therefore, so what you're going to get is 75 minus the 48, which is going to be 27. And then add 27 times 15, which is 405. So that is 405 joules, okay? And this is the net work, right? So we could have gotten this by simply taking the applied and then subtracting this. If you took those, you can try that on your own, you would get exactly the same answer. Now, if you want to be able to round this, okay, so two significant figures, this would have been around 410, right? So it's approximately joules. Now, that is the net work. So this is an interesting question, and it kind of forces you to both think about the applied forces, okay, the constant forces you have, and then any other forces that might be present. Very often in these questions, you might say that it's a frictionless surface, and then therefore you don't have to worry about, the actual work done by friction. And now let's take a look here, okay, on the last one. Based on the information, is the stretcher accelerating or is it in constant motion? So this is another good question. Well, we know, okay, so if you go back in here, so there is a net force. So if F net is not equal to 0, that means, okay, that your actual object, okay, so in this case, okay, whatever you have, is going to be accelerating, right? So that is what Newton's second law says. So in here, it is accelerating. And therefore, as it starts to accelerate, you're going to have this work, so the work by the person done is going to overcome the force of friction. So that force of friction typically turns into thermal energy, just kind of dissipates as heat in some form. And then the additional kind of forces that you had present, basically that energy gets transferred from the person to the object, and if it starts to accelerate, then it's going to get to some particular speed, and then it will have kinetic energy. All right, so this is question number 1. Let's take a look here. So question number 2. So this is a neat question. An object is under a net force. All right, so here is the net force, which is displayed. Now calculate the net work done on the object over the total displacement. So basically this is kind of going back, kind of similar to the previous one, except this is just showing us what the net force is. And this looks like a force and a position graph. So for every single position, it just tells us what the force was. And this goes back to the idea of remembering that work, well, this is the net work because we're talking about net force. So this is going to be the F net, and it's going to be multiplied by whatever displacement you have, right? So that's what we have in here. And if you want to be able to calculate what this work is, okay, so notice that this times this Okay, and then of course it is times the cos of the angle. Now within here, whenever they give you a position, okay, and this is your force, you're assuming that this is either going to be cos of an angle is 0, or the angle is going to be 180. So it's either in the direction or in the opposite direction. All right, so that's the assumption. So this, okay, is going to be either 1 or -1, as you can see there. So you either have positive or negative values. And notice both of them are west and west. Okay, so we don't really need this. So now with that, as you're going to be going along, so you're going to have to do and figure out what the area under the actual, position and then the force graph is. So you can break this down into pieces. So here's going to be your first piece, right? So this is piece number 1, and you can figure out what the work is there because you can find out what the area under that curve is, right? So that's number 1. So I'm going to break this down. So this is number 1, and this is going to be the actual work. Is this, I'm going to put a little 1 there for that, is equal to, and this is going to be the area, which is going to be 30 multiplied by 20. So notice that this is all in meters and newtons. So this is going to be 600 joules, okay, of work. So that's in the positive side, right? So that's easy to find the area because it's just a rectangle. Now next, okay, so what you're going to run into, so you're going to have another piece. So this is going to be piece number 2. That's right there. So number 2, so I'm going to put work number 2. So it's still positive within there, but notice that this area is a triangle. So area of a triangle, which is 1/2. The height is still 30. And then the actual length, so in this case, so it's the actual position, which is going to be, or displacement, is 10. So this is what we have. So this is going to be a 1/2 of 300, and that is nothing else but 150 joules. All right, so that's what you have right there. So again, both are still positive. Now let's keep on moving along. So this is going to be my third piece. So I'm going to go red in there. This is going to be 3, so that's this piece right there. But notice now it's negative all of a sudden. There's going to be 3, so this is piece number 3. So 1/2 because it's a triangle. And it's going to be -20 there. As you can see there, that's the height of that triangle. So that's this right here. So the height right there from here to here. Okay, from here to here. So this is from 30 to 50. That's the displacement that you have, which is going to be also 20. And this is going to be 1/2. Now it's going to be negative. I'll put that in the front. 1/2 of 400, which is just -200 joules. All right, and then we have just one more piece at the end there. So that's going to be this piece. So that's right there. And this is going to be piece number 4 right there. So work number 4 equals, and what we have is going to be just a rectangle, so -20 multiplied by, and this is going to be 10, 20, 30, and this is, so from the distance from 50 to 80, so the displacement, okay, it's going to be 30, which is going to be -600 joules. All right, so there you have it. And now if you want to find out what the net work is, you're going to have to sum them up. Sometimes we'll put summation as this symbol, so summation of all of the works. Okay, so this is going to be from I equals 1 to 4, so that means 1, 2, 3, 4, so that's the summation of all 4 of them, and you can go ahead and add them up. Now, notice 600 plus minus 600, so these two cancel, so that's gone, and notice you have 50, and then this is minus. Okay, so this is going to be actually -50 joules of work. And you might start thinking like, well, -50 joules, what does that exactly mean? And does it even happen? Yes, it can happen. So remember, for example, if you have friction, right? So you have an object which is moving, and then you start to have friction. Even if you let it go, you're no longer applying anything. So friction can actually slow it down. And the work done is going to be in the opposite direction because friction opposes the motion, but the object can still be moving in some way. Anyways, this is not what they've asked. They just asked us to figure out what the net work is, and that's how you would find it. So remember that if you do get these force and position graphs, just remember that work is the area under the actual graph itself. And you can break it down into these pieces, rectangles and triangles. It's typically what you're going to have within foundational courses, and then you can just calculate it exactly what it is. Okay, so that's example 2. Here is example number 3. So this one is going to be, I guess, a little bit of a challenge. So let's see what it asks us. So here's the figure. So it looks like you have a box on the side, a box on a ramp. So it's 30 degrees ramp. So you have 5 meters of height up there. So we can certainly find out how long that actual ramp is. So that's fine. So we can do that. I'll do that in a moment if it's needed. It looks like we have a coefficient of friction there. So this is K, so it's kinetic friction. So that's that right there. Okay, so let's break it down. So part A, the gravitational potential energy. So we want to be able to take this and calculate. So notice calculate. So we want to calculate the gravitational potential energy that the 10 kilogram mass would obtain if pushed all the way up the ramp. All right, well, so you may recall that pushing something up the ramp, right, up to a certain height, so in this case, I guess it's going to be up to 5 meters, is the same thing as lifting something up. So what's the gravitational potential energy of any object? It doesn't matter if there's a ramp or not. All you need to know is, what is the height relative to. So here, I'm assuming, so the gravitational potential energy is going to be relative to that surface that it's on. So either it is, this box or this box, doesn't matter. They're both kind of at the bottom point. So you're going to be lifting this up and it's going to be 5 meters above the ground. Okay, so in order to do that, I actually don't need, to calculate, the actual pushing up, at least not as of yet. But I do need to find out what the gravitational potential energy is. But that is just mass times gravity times the actual height, or the displacement or distance, in this case in the y direction. And if I do that, then this is going to be, 10 kilograms times 9.8 or 9.81, whichever one your teacher uses. Okay, so it's always typically an approximation. And then your height, which is 5 meters. So there you have it. So I can just go ahead and calculate this whole thing. So 10 times 9.8 is 98 multiplied by 5. So it's going to be 490 joules. So that's how much gravitational potential energy this box would have had at the top there. All right, so that's the first part. Okay, let's move over. So I'll just move over to part number 2. What is the minimum work that you would need to do to push the mass up the ramp? Okay, so this one is not going to be as easy. So in order to push this thing up the ramp, so if we want to push this all the way up the ramp, okay, the amount of energy, now because of the fact, so notice in here, because you have friction, so you're going to have to overcome friction. And you're also going to have to overcome the gravity, right? Or at least the component of gravity that's trying to still keep it down. If there was no friction, then actually, so basically by the law of conservation, that you would have that the gravitational potential energy by lifting an item would be the same as pushing it up the ramp. But now, because you do have friction, you're going to have to exert more force, right? To be able to push this along. As you're going through the entire distance. So let's take a look and see what that would entail. So we have a box, so I'm going to put a box, drawing, so like this, so be it. Now let's fill this in here. So we have, so I guess this box, I'm going to try to draw, so this is going to be some triangle in here, all right. Now I'm going to make it a little smaller. Okay, we know that this is 5 meters, right? We know that this is 30 degrees. So one of the first things that we need, so for this box, is we can certainly move it all the way up, but it's coming from the bottom. So for that box, I need to know what the displacement would be. Well, so that displacement, I need to know what this is. Now I can certainly find that out. So from here, so this displacement is going to be, so it looks like it's the hypotenuse, right? So with the angle, so this is going to be opposite, so it's going to be using the sine. So sine of 30 degrees is equal to the opposite, which is 5, all over the hypotenuse, which is going to be your displacement that you're going to move this box along. So in other words, this is just displacement is equal to 5, okay, divided by, and then sine of 30. All right, so sine of 30. Now, sine of 30, so you may remember, or you may not remember, is basically a half. All right, so you can look that up on your calculator if needed. So if that's a half, which is 0.5, okay, so 5 divided by a half is going to be 10. So this displacement is going to be 10 meters. All right, so let's keep it at that. Okay, so 10 meters. And again, so you can, of course, check these things for yourself. So, you know, it's 5 divided by, and this is going to be sine of 30. Okay, if you don't trust me, so there is your 10. Okay, so now we have our displacement. Now, why do I need the displacement? Is because if I want to calculate the minimum work, I have to move this box all the way up, and I'm going to be displacing it by 10 meters. So the next thing I need is what's the minimum amount of force that I need to push with in order to move this box. Now, because there is friction, I'm going to have to overcome friction, and I'm going to have to overcome the actual box's gravity. But it's going to be a component of the gravity. So here, so let's, you know, if I take this out in here, I'm going to just put this box over here. I'm going to draw kind of a free body diagram. So within here, so what we have is, you know, we have our, so this, my force of gravity is going to be down. Now, this is just mass times gravity, right? Now, the component, okay, of gravity in this direction, which I do need, because I need the actual normal force, right? So I need the normal force, so the opposite, which is going to be equal. Remember, the normal force is the same, or it's equivalent to the force which basically touches the surface. Now, I'm going to need that, and I'm also going to need, so along with this, okay, so this right there, well, that's not what I wanted, okay, so with this, I'm going to just shift it. I'm also going to need, okay, so there's a component, okay, of the force, which is going to be in that direction, and that's going to be, so right there, so this is what I have, okay, so that's that, okay, right there, that I'm going to have to, you know, deal with, right? So, or at least overcome. So that's going to be one of the forces, because I'm going to be pushing in this direction. So this is my applied force, right? Now I'm also going to have this force right here. So this component of the force, I'm going to have to overcome here. And I'm going to have to overcome the other force, which is going to be the force of friction, which is also in the opposite direction. So force of friction, this is kinetic friction right there. All right, so I need this one, okay, and I need this one. Now I don't know how big these are as of yet, but these are the two forces that are opposing me that I have to overcome. If there's no force of friction, I would just have to overcome that little one. Now I'm going to call this force, okay, of gravity, okay, and I'm going to put a little prime here because of the fact that it's the component, right, of it. Now, here you're going to have to do and kind of remember a little bit of things with angles. So, you know, don't forget that what you have right in here is the following. So because of the fact, okay, so the angle that you have in here, so I'm going to try to draw this out, okay, right here. So if the box was right on top of here, right, and this is right there, notice that this angle is 30, right? So what that would tell us is that, okay, this is going to be, so as you're going along, okay, and then this is, okay, sorry, the force of gravity is right here, and this is the one that we're interested in. So I have this triangle right there, right? So that's my little triangle right there. And if that's 30, then that's going to be 60, right? And this is 90 because of the fact that you have a triangle and the total angles sum up, okay, to your total, okay, of 180. And now this particular component, okay, so that's what you have. This angle down, so what you have is, you know, this, okay, is basically your force of gravity, okay, that's what you have. And now this is what you want to obtain, okay. And now notice that this angle is just 30, right? Because right here, if this is 60, then this is going to be 30 because they sum up to 90 because they're at a right angle. So what that is telling me that this particular component, right, which is this component, which is what I want. So that component right there, so if I go back in here, this is going to be just mass times gravity because it's this, right? And then the angle, so notice it's going to be cos, okay, of that angle. That's this piece. And this piece is going to be mass times gravity, and it's going to be sine, okay, of the angle. So that angle is 30 here. That's what you have right there. Okay, so now I have pretty much everything that I need. All right, so let me just add a little page here within there so that I have more space. Okay, so now let's get to it. Okay, so my goal is, okay, so force applied equals, I don't know yet, but the minimum is that I have to overcome the force of friction, which is going to be mu times your force normal. So that's by the friction equation. You can put up a link up above there to that, dating you back to dynamics. So this is going to be, so now notice we have 0.25. 0.25 multiplied by, now my force of normal that I have. So that's going to be equating this because this box is not falling down. So these two are equivalent to each other. So that's going to be mass times gravity. And then this is going to be cos 30. All right, so I can obtain exactly what this is. Okay, and so I'm going to leave it for the moment. And then my force, okay, of gravity in that direction. So that's this little piece, which is this right there. So that's opposing it. Okay, so within here. So that's going to be equal to mass, gravity, and sine of 30. All right. So there we have it. So now I have all my forces. So that means my FA, okay, is going to have to be at least, okay, equivalent to these to get this thing up and moving. Okay, it's going to be a little bit above it. Okay, that's what I will have. So it's going to be the summation of these. Now, once I have that force, I've just found the displacement. So I have the displacement right there, which is 10 meters, okay, multiplied by the force that is applied. And that would be the total work which is done. All right, so let's calculate all of these. So it's going to be, so 0.25 multiplied by the mass, which is 10 kilograms, multiplied by 9.8, multiplied by cos of 30. So there we have it. So that's going to be, 20, that's 21.2176, 22, etc. You can keep a few decimal places. The second one that I have in there is going to be mass, which is 10, multiplied by 9.8 times sine of 30. Well, that's just a half, so this one is easier. That's going to be 49. So your total force applied is going to be equal to, the 21.2176, etc., plus 49. Okay, so that's that answer, plus 21.2176, whatever. It's approximately 70.2176. Okay, if you want, you can keep a few more. And therefore, the work needs to be applied times the displacement. And that's going to be equal to, so in this case, the 70.21 multiplied by, this is going to be 10 meters right there. That's what I have there. So that's going to be approximately, 702, 176, okay, etc. So it's about, 700 joules. Okay, and if you want to write it to two significant figures, just put it in scientific notation. Okay, in this way, so that the mantissa will have two significant figures. All right, so there you have it. That's the amount of work. Now notice the amount of work is more, right, than if the surface was just frictionless, because then it would have been just 490. Okay, that's all that you would have to do. And in fact, you would be able to see that, okay, within here, because notice that means we would just have to overcome this force, which is 49, and we would have to take 49, and then the displacement was 10, which was 490 joules, okay, in total of work. And that would have been the same thing as we had here. But because of the force of friction, we have to, unfortunately, do more work, right, to overcome that. Okay, so that is part B. Now let's keep going. So part C, if the gravitational potential energy is the desired energy, okay, then how efficient was the process of pushing the box up the ramp? Okay, well, this is much simpler now to do once we have this. This would have been part C. Well, efficiency is equal to the energy which was desired, so the energy out, okay, divided by the energy that you had to input, so that would have been the amount of work we had to do, times 100%. So in this case, this is 490 divided by, so approximately, I'll just put it back to 702, okay, joules, so give or take, times 100. So let's see how efficient that was. It's actually not bad. Divided by 702, so it's about 70%, so 69.8. Okay, so 69.8%, okay, or 70% if you wanted to have it. So that's the efficiency that you would have. You would have all the other energy kind of being utilized, okay, to overcome that friction. Now, where do you think the extra energy exerted to do the work, to overcome the friction, transforms? So because energy is always transformed from one form to another, if you're pushing it, so the chemical energy within you, it's transferred in, okay, into mechanical energy, so you can push this thing up. And that 30% of that inefficiency, so 70% will go pretty much to the potential energy of that object, right, as it being kind of placed up there. But the other one most likely is going to get dissipated or transformed to thermal energy. And that's what mostly friction will do. So that's why you see things heating up, because thermal energy has something to do with increasing the temperatures, right? Okay, so the answer would have been primarily goes to thermal energy. Now, if you were capable of pushing the mass up the ramp in 15 seconds, then what was your power output? Okay, well, so that's pretty good. Now, so it tests our understanding of power. So let me go back in here. So this would have been part E. Well, power is just equal to the amount of work or the energy, okay? So it's the change in energy, okay, over the change in time, right? Or in other words, okay, the work, okay, over that. Now, we have done about 700, let's still keep it at 702 joules divided by, and this was, they said 15 seconds, so 15 seconds, so therefore the power, okay, within here, so if you would put that in here, 702 divided by 15, 46, about 47 joules per second, or watts. That would have been the power output. Right? So that's the last one. This is a really good question, a really tough one from the viewpoint of part B, because it forces you to understand, okay, and then work with the actual forces and angles. So most likely in grade 11, maybe you won't get pushed to these limits, but I think if you understand this, it's definitely a huge advantage for you as a student to be able to work such questions out. All right, let's keep going. So here's question number 4. So calculate the mechanical energy, kinetic energy, and gravitational potential energy. All right, we'll do all of those. Sounds good. So mechanical, kinetic, right there, and gravitational, right? So don't forget, mechanical energy is the summation of kinetic energy and gravitational potential energy. And we want to find it at positions A, B, and C on the roller coaster. So here's A, B, and C. All right, so we have all of these, A, B, and C. And so assume that the mass, okay, so here's the mass. And then we're going to neglect, friction and air resistance in the problem. So hint, use the law of conservation. Yes, definitely do. Okay, so let's start up with A, because that's what's given. Notice that we do have the speed here. So I'm going to put, so for A, we have, so our kinetic energy, okay, at A is going to be equal to 1/2 times mass, and then whatever speed we're going at. Okay, so this is going to be, so I can substitute all of this in here. Okay, so 1/2, which is 0.5, times the mass, which is 385. That's straight from the problem. And then times, so 14, and this is squared. Okay, so quite a bit of energy there. So 37730. I'm not rounding anything at the moment. So that's that. The gravitational potential energy at A, okay, so that's going to be mass times gravity times the reference, so the displacement, okay, or the height that this object is at. So let's do that. So 385 times 9.8 times, then we need the height, that's 35 meters for A. Okay, so it's, again, quite a lot. All right, so there you have it. Which means that your mechanical energy at A is going to be just a summation of these two. So you can add these up together. So it's going to be your answer from that, plus 37,730, 169,785 joules. All right, so that's what you would have there. Now, let's take a look at B. Okay, so point B. Okay, so let's see what that will entail. Okay, so within here, so my kinetic energy, I won't know right off the bat because I don't know the speed at that point, right? But I can use indeed the law of conservation. So your mechanical energy at B is going to be equivalent so long as there's no frictions, okay, and transfers to any other energy. So that means that this will not change at any point. In fact, it's the same thing on C as well. Your gravitational potential energy, well, we can calculate this because we do know what the height is there. So it's going to be your mass times 9.8 times the height of 18, which is going to be 67,914 joules. And therefore, now your kinetic energy, we don't need to know what the speed is. We can certainly find out what that speed would be if needed. But first, we can take our mechanical energy at B and subtract the gravitational potential energy. Okay, so here at B, maybe I'll put these B's in here. And what that would give us is the leftover energy, which must be transferred to kinetic energy, okay, due to the law of conservation. So 169,785 minus and 67,914. So this is how much we would have. Okay, so this is what we would have. Now notice it's more than what we started with. And of course that should make sense because it's our gravitational potential energy. If you're going down, it's going to get transferred to kinetic energy. So we're going to be going even faster. And this is definitely, if you've been on a roller coaster, certainly notice that as you go down, you pick up speed. Okay, so there you have it. So that's at part B. Now at part C, so this would have been your last one. Maybe let me shift this out of the way. Okay, so this would have been for part B. Now for part C, now we're going to go back up there. So our mechanical energy, again, there's no change there, so that's going to stay the same. Again, because of the law of conservation. Your gravitational potential energy, okay, at C, well now, so this one you can certainly figure out because of the height given. So it's 385, the mass, 9.8, and then multiplied by 25. That's 94,325 joules. And now again, so the subtraction of the two is going to give us the kinetic energy. 785 minus 94,325. Okay, so that's going to be your kinetic energy. at C, which is 75,460 joules. Now, if you wanted to round all of them to, as many, well, it looks like 2 sig figs again, you can do that. But I'll just leave this because it just nicely captures all of this for us. So we have what we need. Now, by the way, if you wanted to know what the speeds of these instances were, so don't forget that kinetic energy is just 1/2 mass, velocity squared. So if you have this and you have the mass, you can certainly solve for V, right? You can take the square root of both sides as you kind of isolate to find out what the speeds were, if that's what they asked. They actually didn't ask us here, so I'm not going to do that, but maybe I should have put that in here. I definitely wanted to point that out. And this is all about the law of conservation. There isn't anything else that you need. So this is a really nice question to be able to solve. All right, so here's the last example to close this off. And this one doesn't look like it's a bad one. So a typical laptop is rated at a power of 85 watts. So it looks like it's a power. So if we write down the given, so power is 85 watts. If you have been using the laptop to do your homework for 3.5 hours, so this is your time, so 3.5 hours, then how much would this cost you if the current energy usage is, okay, so that's interesting. It's like paying your bill. So it's 8.5 cents, okay, per kilowatt hour. Okay, so for every 1 kilowatt hour, that's how much you would pay. And I don't know exactly how much it is now, but it's give or take something around there. So now how much would this cost us? So this is an interesting question. So first, notice that it's kilowatt hours. So now kilowatt hours is a unit for energy. All right, so it is a unit for energy because kilowatts, kilo just means 1,000, right? Okay, watts just means joules per second. And hours, so times hours, so notice that you have, okay, if you do this, your times, you can certainly convert hours to seconds, and then you can find out how much energy in joules this would be. Now, we don't need to do that, actually, because of the fact that this is in watts, this is in hours. So what I'm going to do is I'm going to say P multiplied by T, all right, so power, so this is coming from power is equal to the change of energy over the change in time. So if you bring this over on the other side, you're going to get energy is equal to P, times T. That's what I'm doing here. That's my little delta T there. And with this is going to be 85 watts. I'm not going to convert this to seconds because of the fact that this is in kilowatt hours. So what I'm going to do is I'm going to multiply this by 3.5 hours. And so just bear with me. So this is going to be 85 times 3.5. So this is going to be 297.5 watt hours, right? Watt hours, because they're multiplying. Now, I want kilowatt hours. So, well, kilo is 1,000. So that means that this is going to be 0.2975 kilowatt hours. Again, don't forget. Okay, 1 kilowatt is equal to 1,000 watts. So if you do that conversion, this is what you're going to get. And now from here, I can multiply this because it's 8.5 cents for every 1 kilowatt hour. And that now cancels, and I can find out exactly. So let me take this answer divided by that times 8.5. And it's going to be a few cents, so about 2.5 cents. Okay, so it's not going to cost you too much. But, if you have billions of laptops running all the time, it starts to add up, right? So there you go. So that's what you actually have right there. And that would solve your last example for this test. Okay, we survived. Thanks for watching. See you in a future video. Bye, everybody.